This now will have an important corollary as well, the proof of which I will leave as an exercise to you. Now, of course, we have shown the existence of maxima and minima. But, so there's at least one point x upper star such that f of x star is equal to max f of k. But it need not be unique. So the question now is, what can we tell about the structure of the set of maximizers as well as the minimizers of a continuous real-valued function on a compact set? The set of maximizers and minimizers, they will turn out to be compact subsets of the domain space as well. So let x tau be a topological space. K, a non-empty subset of x, f on k to r, a function. Assume that K is compact and f is continuous on K. So we have all the hypotheses of the theorem. Then the set of x stars in K such that f of x star is equal to the maximum of f of k and the set of all x lower stars in K such that f of x lower star is equal to the minimum of f of k are both compact. But how would you proceed about proving this?
Yeah, it's bounded because it's in K. They lie in K, so of course they are bounded sets.
No, but this compactness is in x tau.
Okay.
Heine-Borel does not work.
Okay.
Okay, so these are subsets of cap K, which is considered under the relative topology with respect to tau.
Definition.
Definition, but we have an important theorem which will simplify this.
Isn't it that K is totally bounded and closed? Can we use?
Well, just closeness, would that not suffice? We have a theorem which says a compact set need not be closed. Fine, but every closed subset of a compact set is compact as well. K is compact. These are subsets of K. So the whole thing actually reduces to showing that these sets are closed. And well, closeness, on the other hand, is reduced to containing all the limit points. So, well, then the thing is to show if something is a limit point of the set of all maximizers, then it must be a maximizer as well. Huh? Okay. So that takes care of this section as well. The next section, well, we'll consider complete spaces, because we introduced the notion of total boundedness. We have seen compactness implies in metric spaces in general closedness and total boundedness, but the converse was not true. But the counterexample that was provided by Q, which seemed to have lots of gaps in its set structure. So it was not intuitively not complete. And we said we will single out a subclass of metric spaces in which actually the equivalence between compactness and the conjunction of being closed and totally bounded, that will be reestablished. That's complete spaces. That will be the end of this introductory chapter on elementary properties of Euclidean spaces. Now we're interested in optimization. Well, so far what we have got is something important, but it's just about existence. Well, how can we find them? So far, there is no clue at all about how to find them. How do you find them? Well, you need differentiation for that. So the chapter which will follow complete spaces, the section on complete spaces that we will start to deal with now, well, that will be on differentiation. But we're interested in functions on Rp to Rq. Neither P nor Q need not be 1. If they're both 1, well, we know from calculus how to differentiate. If the range space has dimension 1, then that's, well, a real valued function of several real variables. There we know partial differentiation. Well, say from advanced calculus. But if Q is larger than 1 as well, what will happen, we'll see next week. But let's get back to our work. This is 1 point something. I forget counting it. Complete spaces. Now let's start with an example. Let's consider this sequence. Now let me write it like this. N will be a natural number. Well, this will be an irrational number. We know square root of 2 is irrational. Well, if square root of 2 over n is rational, then square root of 2 would be rational as well. So this is irrational. Now let us consider the subspace of R under the usual metric. Is this sequence convergent in this space? No. Let's remember convergence of a sequence in Xn. If Xn is a sequence in X, it's convergent if and only if there exists some A in X with Xn converging to A. If we read this general definition back in this context, for this to be convergent, there should exist an irrational number, say A, such that this converges to A. In RD, where does this converge to? To 0. Well, if this converged in R minus Q D to some A different than 0, then that would actually contradict the uniqueness of limits of sequences in RD. So this is not convergent, or let me write it here, not convergent, divergent in R minus QD. Okay, but, well, if I say divergent, fine, it's divergent according to this definition, but you can have a sequence which has a wild variation and is divergent for that reason. This is very close to be convergent because it's convergent in a larger space. But then the question now is, can we describe that fact which I just mentioned by entirely staying within the limits of this metric space without making any reference to R which contains that? Suppose we only know R minus Q. We do not know rationals, we do not know reals, we're in here. This is not convergent, divergent, but it looks close to be close, conceptually close to be convergent. Well, if a sequence converges to a limit, then its terms eventually get closer and closer to that limit, fine. But now that limit is missing. Can we still derive something from just what being said in terms of the sequence only? If a sequence is convergent to a limit, not only do the terms of the sequence get arbitrarily close to the limit, but they also get arbitrarily close to each other. So we'll take that to define the notion of a Cauchy sequence. Now let X rho be a metric space and Xn a sequence in CapEx. Now we say that Xn is a, well, sometimes it's referred to as a fundamental sequence as well. I mean, in different textbooks. So is a Cauchy sequence if for every epsilon positive from some point in the sequence on in the tail, all the terms get closer, epsilon close to each other. There is some k in n such that, now I have no limit, no candidate for the limit, but any 2 points, that is, for all mn, both larger than or equal to k, we have that rho xm, rho xn, that gets less than epsilon. Okay? Now let's see the simple example that we started with, and let us show that it's a Cauchy sequence in the metric space of irrationals under the usual metric. So we consider square root of 2 over n in R minus Q d. Well, let epsilon greater than 0 be given. Now we need to find some cap k such that no matter what two naturals I take, larger than or equal to that, this should be the case. But here the idea is, we know this converges to 0 in Rd. What does that mean? Well, that becomes arbitrarily small. So given any epsilon, I can find a large enough k such that square root of 2 over cap k is less than epsilon. This is also referred to as the so-called Archimedean property of real numbers, but okay. Now, there is some k in n with square root of 2 over k is less than epsilon. Now let us take any two naturals larger than or equal to cap k and check whether that works or not. Take any mn in n with mn larger than or equal to cap k. Well, one will be larger than the other, and well, with say m larger than or equal to n without loss of generality. Now, d is here our metric. d square root of 2 over m square root of 2 over n. But that's just the usual metric, so this is square root of 2 over m minus square root of 2 over n. But if I perform this, well, I can take this out, and then I'll have n minus m divided by mn. Okay? This is the common denominator. Now this is, I took m larger, this is equal to square root of 2 times m minus n divided by mn. But here I can make this larger by leaving out this part. This will be less than or equal to square root of 2 m over mn, but that is square root of 2 over n, but n is larger than or equal to k. This will be less than square root of 2 over k, and that will be less than epsilon. So, square root of 2 over n is a Cauchy sequence in R minus Q d. Now, how is being a Cauchy sequence related to convergence of that sequence? Do we know something about that so far by what we have done in the last 10, 15 minutes? A Cauchy sequence need not be convergent, because this is a Cauchy sequence which is not convergent in the set space, but it's a Cauchy sequence in that space. But what do you expect about the converse? Will all convergent sequences be Cauchy sequences? Yes, I mean, what we expect is if they all get closer and closer to one and the same thing, then among themselves, they must be getting closer to each other as well. But now let's write that down as a proposition. Now let X rho be a metric space, Xn, a convergent sequence in X with X, well, just a convergent sequence in X. Now, Xn is a Cauchy sequence in X rho. Proof? Well, since this is a convergent sequence in X, well, it converges to some limit. Well, we wish to show that it's a Cauchy sequence. Let us then take any epsilon positive and show that the condition here holds. Let epsilon greater than 0 be given. But what we know is, since this converges to A, then from some point on, its terms will be the distance of the terms according to rho to the limit. They will be less than any prescribed positive real number. So in particular, for epsilon over 2 as well, because what we'll do is naturally we'll take 2 points, xn, xm. We'll consider the distance of xm to A and the distance of xm to A with respect to rho, and then conjoin them via the triangle inequality. There is some k in n such that for all n larger than or equal to k, rho xna, that will be less than or equal to epsilon over 2. But as we have seen, this same cap k will do the job for this sequence being a Cauchy sequence. Now take any mn larger than or equal to k. Now, rho xm xn, that is less than or equal to rho xma plus rho a xn, but they will be both less than epsilon over 2 each, and that will be less than epsilon, so xn is a Cauchy sequence in X rho. We will refer to spaces, to metric spaces, where being a Cauchy sequence and being convergent coincide as complete spaces. Because here, as we have seen, why complete? Well, the limit of this is lacking to be a member here, in here. There is no member in here. Well, although they get closer and closer to each other, the sequence is not convergent since there is the lack of a member in this set to which they all commonly get closer. Well, so it's incomplete. Something is lacking. So that's why the name complete space comes. Let X rho be a metric space. We say that X rho is complete if every Cauchy sequence xn in X rho converges to some point A in X. Now I said convergence and being a Cauchy sequence, they should coincide, but that's equivalent to that since we already know convergence implies being Cauchy in all metric spaces. Now here we'll continue with showing that Rn under its usual metric is complete. We know at least one example of an incomplete space. It's R minus Q under the usual, but Q under the usual metric, will that be complete? No. You can actually construct a sequence in Q which is not convergent in QD. Well, take any A in R minus Q. Take a one ball about this. Will this contain a rational number? Yes. Take that, X1. Then take 1/2 ball. Will that contain a rational number? Well, for each n, take the 1/n ball about this irrational number. Pick any rational number from that 1/n ball, but that xn, that will be in Q, but you can easily see that it will not converge to any rational point because we have taken this to be irrational. Okay, but we'll prove that Rnd is complete. We'll start with that the next hour on Tuesday at 8:40. Then, well, we'll see some small results concerning complete spaces, but the big theorem will be, in a complete space, a set will turn out to be compact if and only if it's closed and totally bounded. But then all of a sudden, we will start to see something which will make us unhappy about complete spaces. We will see that completeness is not a topological concept, actually. In fact, you can have two metrics, rho and rho prime, which are equivalent topologically. They induce the same topology, but X rho might be complete while X rho prime is not.
1/x in R. Huh? 1/x in R, maybe.
Well, in fact, I will give I will give an example in written form as a handout because that might take too much time in here, but we'll have an example of that, okay? So I guess we can stop at this point.